of us are doing fine. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. In our discussion today, I'm going to look at a very important concept which is going to be widely applicable in physical sciences and mathematics. And this is going to be forming what we refer to as a Euler's number. In our previous discussion on the concept of decay curves and, of course, exponential curves, we have come across a number or a symbol given as such. And this specific symbol is going to play a fundamental role in trying to assist us evaluate various aspects which are going to be requiring an aspect of either decay or exponential growth, which I've just mentioned. Now, in this particular case, we are also going to see that this specific aspect is going to be widely applicable in various aspects and topics in logarithms. And of course, this is going to be forming a basis for us to try and understand basically what this specific aspect of the number E is. Now, we are going to consider an expression of the form which can be given in terms of a plus x raised to the power of n. And we're going to see that in this particular case, we're going to consider the value of n, which is going to be forming a set of real numbers. Now we're going to consider this specific expression and see whether we can express it in a form that is given in terms of a binomial series. Now in this case, we are going to have this specific expression given in terms of the raising powers of n, where n, as we have said, is going to be forming a range of course, this specific aspect of real numbers. Now in this case, then we are going to have the expression of a raised to the power a plus x raised to the power of 0. And then this is going to be giving us 1. Now this is an implication that basically a number raised to the power of 0 is going to be giving us 1. So we shall proceed and have this expression given in terms of a plus x given as such. And of course, if we increase this power to 2, this is going to give us 2ax plus the x value of the square of x. And perhaps we can consider the last one for a raised to the power of 3, which is basically equivalent to 3a squared x plus 3ax squared plus the cube of 3 given as such. And these are going to form a range of values with different coefficients. Now, if we try to consider these coefficients, we're going to have this first expression giving us a coefficient of 1. And the second one is going to be giving us a combination of the first term for 1 and 1 given as such. So the third expression is going to be giving us basically a coefficient of 1, 2, and 1. And the last one is going to be giving us 1, 3, 3, and 1. Now, if we try to look at this one, this is going to be forming what we refer to as a Pascal's triangle, which is going to be basically be given by this specific combination of the coefficients which we have just considered above. Now, in this particular case, we can consider this particular expression being given in a general way and try to see what is the general range which we can give for an expression of a series of numbers which are going to constitute a range of values of n, where n is, of course, as I said, a member of the real numbers. Now, then we can have this expression given in terms of a plus x raised to the power of n, and this can be expressed in the form of this combination whereby we're going to have n o. These are going to be, of course, the derivations of the concepts of the combination rule, which I'm going to be mentioning shortly after this specific, of course, evaluation. Now we're going to have this value of a raised to the power of n and x raised to the power of 0 as our first term given as such, and then we are going to have this one expressed as such for the subsequent values, whereby we're going to have x raised to the power of 1 plus n 2 a n minus 2 x raised to the power of 2 plus n 3 a n minus 3 x raised to the power of 3. And we can express a specific value of this particular range by considering the value of this specific real number which we have given, by giving it a specific, just a general representation given as such. So this is going to be given in terms of a n minus r, and then we shall have x raised to the power of r given as such. So if we combine this one, we are going to have a last term being given in terms of n minus n, and then we shall have this specific value of a raised to the n minus n x raised to the power of n as our last term in this specific expression. So we can simplify this particular expression and give it in form of a similar way. Now, if I consider this specific set of expression whereby we're going to have this particular combination giving us 1, And basically I said that n number raised to the power of 0 is equivalent to 1. Therefore, I'm going to expect that we're going to have a simplified version of this specific, especially for the first and last term, which are going to be given in this specific format. So we shall have this expression given in terms of these respective terms, whereby we're going to have the first one given as such, and the second one can be given in terms of n1 a raised to the power of n minus 1 x raised to the power of 1. And this is going to continue to a particular value which we can generally represent as n r a raised to the power of n minus r x raised to the power of r. And as we said, of course, this is going to go and form the last term, which is going to be given in terms of x minus, of course, n given as such. So this is going to be forming what we refer to as a finite series. And this specific finite series was, of course, going to be forming this particular coefficient. Now we can consider a general case whereby we're going to have a particular evaluation which we can, of course, simply work out using a particular, of course, finite series which you have come up with on the board, whereby if we have an expression of the form a plus x, and we're required to express it up to the fourth term, then therefore we're going to exploit the same concept which I've mentioned. Now, basically, the first term is going to be appearing in the form of a raised to the power of 4, and then we're going to have n, of course, 1 given as such. Sorry for that. So in this case, we have said that n is going to be forming this specific value of a fourth term, which is going to be given as such. So therefore, we're going to have a 4 minus 1 x raised to the power of 1, plus we're going to have 4 2 a raised to the power of 4 minus 2 x raised to the power of 2, and then we're going to have 4 3 a raised to the power of 4 minus 3 x raised to the power of 3, and then we're going to have our last term given in terms of 4 4 a raised to the power of 4 minus 4 x raised to the power of 4. So this has been expressed in a form which we have basically come up with on the board concerning the finite series. Now we're going to see that there's going to be a unique set of values which we're going to be expressing in terms of a specific combination, and this is going to be forming what we refer to as a combination rule. Now therefore we can give this particular combination in terms of these specific values of nr, which is going to form what we refer to as this specific ratio of n factorial n minus r times r factorial given as such, and this can be expressed in a form of the combination of nr CNR given as such, which is going to be giving us the value of n factorial all over n minus r factorial given as such. So this is going to be given a particular name which I've basically said is a combination rule. And we're going to use this specific combination rule in order for us to find these particular values which I've just mentioned on the board. And if we consider an expression of the form which we can give in terms of a general representation, so I'm just going to give a general representation for this equation, since we have considered a specific one. Now, if we have an expression of the form which can be given in terms of 1 plus 1 all over n raised to the power of n, this can be expressed in form of this particular finite series which I've mentioned, and this is going to be forming our first term, our second term, and then we're going to have n into n minus 1 of this specific term times this specific value for 1 over n, the square of that, all over 2 factorial. And this, of course, we're going to have it with a combination of n into n minus 1, n minus 2, all over 3 factorial. But in this case, we're also going to have 1 all over n raised to the power of 3, which is going to be forming. So basically, this is specific last term, which is going to be, of course, a combination of this one is going to be 1 all over n raised to the power of 3 given as such. And this is going to be forming a specific series which is going to be catering for all the values of 1 to, of course, the first term to the nth term given as such. And this can be further simplified into a version of the form which we are going to have as n plus 1 plus this value of 1 minus 1 all over n. And this is going to be all over 2 factorial. So this basically is going to be 1 minus 1 all over n. I hope it's legible from your end. And we're going to have this one as a combination of the value of 1 minus 2 all over n plus 3 all over n, the square of n given as such. And this is going to be all over 3 factorial given as such. So basically this is going to be 3, and then we're going to have 2. And this is going to be forming our 3 factorial as such. So if we consider this specific value to a range of terms which are going to be considering values of n, which are going to be a set of real numbers, we're going to see that as or in the limit as the value of n tends to infinity, we can express this specific expression using this particular representation, whereby as n tends to infinity of the expression of 1 all over n raised to the power of n. This can be given as the first term plus the second term plus 1 all over 2 factorial plus 1 all over 3 factorial. And this is going to be going on to those range of values that is going to cater for all the values of n. Now, in this specific case, we're going to see that these particular values were worked up to the 20th term. And of course, the number which was found, or the expression which was found, of course, was rounded up to, of course, 36 decimal places. And the number that was found to be given this specific value for the, perhaps I'm going just to give this to 3 decimal places. And this specific number that was found, which was, of course, for the first, it's going to be for the first 20 terms. First 20 terms of this specific series were worked out. And then it was found that these first 20 terms, they are neither recurring nor are they going to form what we call an exact value. And then this specific, of course, a number was seen to be what we refer to, was considered to be what we refer to as an irrational number. And this specific number was given in terms of this specific representation, which I've given in terms of E. Now, in our day-to-day application, we're going to come across this specific number given in terms of 2.718. And this basically implies what we refer to as a Euler's number. Now, this number is going to be widely applicable in the various fields which are mentioned in our opening statement of this specific discussion. And we are going to sum up this particular representation for the number using our general expression, which can be given in this specific case. So we are going to have this one given in terms of this specific representation, whereby A can be given as a summation from n is equivalent to 0 to infinity of 1 all over n factorial given as such. So in our particular representation, then for the equation which we are given for its derivation, we can give us n tends to infinity of this specific expression. We're going to have this one given in terms of 2.718, which is going to be forming our Euler's number. So I hope that we have understood this specific procedure. Kindly follow our description boxes. There's a link I'm going to put there for similar discussions, and engage us in the comment section, subscribe, and also ring that notification bell for other updates. That is it for now, guys. Bye. God bless you. Catch us in our next video.